What I'd like to show you now is an example of a roadmap problem from test 4. And the roadmap problem you'll see will follow pretty much the same kind of format. What you've got is a Dieckmann condensation that gives two products because we have an asymmetric diester here. And then we treat this with a couple of things that look like an acetoacetic ester synthesis. So we replace one of the hydrogens on the beta-keto ester. We hydrolyze the ester group, and then we heat it and we decarboxylate it. So you'll see something similar on the test. All right, let's take a look at how you would handle it. What I would do first is draw out the compound, and I'd actually draw it out twice. And then what I would do is number each chain. And you can see that each of these is a 7-carbon chain. So we are expecting a 6-membered ring as a product. And this is confirmed because we already have one of the products down here. And we know that that's got a 6-membered ring. So our thought that this will create a 6-membered ring is also pretty valid. So next we want to figure out what kind of Dieckmann products these will form. So what we know is we're going to get a 6-membered ring. We also know it's going to be a beta-keto ester, which means we're going to have a C-double bond O on one carbon, and on the adjacent carbon we're going to have an ester grouping, C-double bond O with an OMe group. And then we can figure out how it might join, and one of these will be a 6-to-1, and as I was describing in my earlier mini lecture, if this is the high alpha carbon, then this will be 6, and this will end up being 1, so then we can fill out the rest of the numbers. And on this one we'll do the same. Figure out the kind of product we're going to get. And the join will be from 2 to 7. So we know that this will be the 2 and this will be the 7, the 2 being the alpha carbon, or the carbon next to the ester group. Filling in the rest of the numbers. Now we can go ahead and just plonk on the substituent groups. At the 3 we've got a methyl, at the 4 we've got a cyclobutyl, and then at the 5 we've got a cyclopropyl group. And on this one again we'll have the 3 methyl, 4 cyclobutyl, and the 5 will be the cyclopropyl group. So you can see the products we're going to get from that. Now if we go through and we do the other steps on these, you'll see where we end up. So we're going to go ahead and do the addition of the sodium methoxide and then the alkyl bromide. Now the attachment will be between the two C-double bond O groups. We've got a C-double bond O group here. Even though I haven't drawn it in, there's a C-double bond O group here as well. So this alkyl bromide will end up being joined right in here. I'm going to go ahead and do that. Alright, and then we'll have the cyclopropyl, cyclobutyl, and then the methyl group there. And on this one we'll have this, and it'll be the same deal. The alkyl bromide will attach in here, and we'll have a methyl, we'll have a cyclobutyl, and we'll have a cyclopropyl. In the next step, the ester will end up being hydrolyzed. And that will be hydrolyzed to the carboxylic acid. None of the other substituent groups change. And I'll do the same thing down here as well. Now the overall strategy here is I'm figuring out what all the products would be, and then at the end I'll find out which one matches this product, and then I'll be able to go ahead and write the letters on all of the products that I've formed. I think this is the easiest way of performing the problem. Alright, so in the last step we decarboxylate, which means we're heating it, and that gets rid of the C double bond OH group, and this is all in accordance with the acetoacetic ester synthesis. If you want to go ahead and review that, it might be helpful. Alright, and this one will do the same thing. I'll move this over just a tad. And that'll be here, and this will be the cyclobutyl, and this will be the cyclopropyl. And we'll have CO2 as a product as well from that. Alright, so you can see what the effect of the decarboxylation is. It just removes the C double bond O with the H group, and we end up getting a ketone as a product. So now that we've got these two ketones as products, I just have to match one of these ketones to the one we have here, the one that we're given. And you can just do this by looking at the order. So we've got a C double bond O followed by this long chain with the square at the end, followed by a triangle, followed by a square, followed by a methyl group. And the one that matches would be this one, C double bond O, chain with a square, cyclopropyl, cyclobutyl, methyl. Whereas this one down here doesn't quite follow that pattern. It goes with this group here, followed by a methyl, followed by a cyclobutyl, followed by a cyclopropyl. So that's not the one that matches here. Now we can just go ahead and put our letters on. So we know that this one's going to be E, since that leads to the one that matches. And this would be D. That makes this one A. And over here, this one would be B, and then this will be C, this will be F, and this final one here, this one will be G. Alright, and so that's how you can most easily find out the identities of A through G.